and I'm going to give you a break in something like 15 minutes. Okay. So once again, yeah, we're talking about the different types of the flow. Depending on your application, we're always looking for the massive flow because this will be the ideal case that the whole system will be emptied by the use of the gravity. For the thinner flow and for the expanded flow, we're going to have a certain type of the accessories like the vibrator or the air blowing. Then we can empty the whole system. But this will be an extra cost on the system. I will show you later some photos that some people actually damaging the silo by trying to empty it. Again, to ask a general question, what do you think that if you're going to have a similar case, the material has been built up here and you cannot take it out, what will be the first thing coming to your mind? What will be the first thing coming to your mind to try to solve the problem? I will make it much easier. Now I filled that with milk powder, for example, and I know it's not supposed to be done, but I start to empty it and I have some, the material is stuck. What will be the first thing I'm going to do? Sorry, yeah.
We'll probably like shake it, tap it, yeah.
Yeah, and don't have it. Now, if it's silo, don't have it. Because I'm going to show you later some photos where the silo has been tapped and actually got damaged. Because usually the lower side, when we have the hooper, it should be very uniform surface. Otherwise, we're going to increase this degradation in the future. Because when you knock it, you're going to have some irregular surface at the bottom, which is going to work as a break or barriers for material flow. So in real life, if you have one of the worker in the place you work at, they start to knock the hooper to get out the material, just terminate his work. Don't let him work there anymore because it's going to cost you a lot of money. Okay, so we said here that we have in the massive flow, all the materials are going to be moved in the bin at the same time. And the fuel flow, the material is going to be only moved fast in the middle, and we're going to have the material stacked up on the sides. And the expanded flow, we're going to have a combination of both the massive flow near the hooper, and above that, we're going to have some separation material. Sometimes this can be used to control the flow, but usually we don't want to keep any materials inside because this will be a dangerous case. The three cases to be shown more accurate is going to be like that. So we're not going to apply any plug flow with the equal velocity. The materials is going to be in motion along the walls, and the fuel flow, we're going to have the active movement of the flow is going to be just in the center, and this will cause something like what we call the rat hole. While we're going to have non-flow materials on the side, this can be either due to the build-up of the materials or the high friction with the wall, and this will make it in static flow. The same thing, we said that in the expanded flow, this is the third flow it's going to have on the side, the material not going to be moved, and in the center we're going to have the material moved. This also going to cause many problems for your system. Fluid-design silo is going to have natural alcohol and the understanding of the solid installed. So you always need to know all the properties, all the materials you have. We never using tables or charts to decide what is the characteristic of the material. We always depend on tests similar to the one we just did in the lab today. Now, if you are going to work in a storing facility, and they're going to bring you the coal, the first thing you are going to do, you will learn that, of course, by starting the work there. The first thing you will do is go take samples, and take these samples to the lab, and you start to do the test for them. You're going to have your own value for the delta and delta wall and do your calculation, and you're going to do that on the next day, third day, and the fourth day, until, thank you very much, until again to have the appropriate cases for the materials, and you will know when you have to remove the materials from the silo or the. So 5 possible conditions will occur as a result of the no flow, the erratic flow, the flooding, the counter current flow, and the segregation as a possible condition we have for the bad design. So clearly, a no flow condition negatively affects your process. We're not going to have the correct amount of the materials to feed the process. And this condition can occur only when you try to initiate the flow by the opening gates or the starting of the feed. We said that the wrong flow can cause a problem. Now, we said once again, this one is developing result of massive flow developing into the silo design structurally for the fueling flow. What's happening is that the high velocity of the material flowing from one side causes that the material segregate on the other side, and this causes the system to get collapsed. Now, this is another example of the process we talked about. We just use the side emptying device. So the material start to have massive flow on one side, and this causes to have the uneven loading for the system, and this causes the system, the silo to be collapsed. Now just imagine, remember once again that this system, though it's built of stainless steel, but the structure always going to be weak. This system has been designed to take the pressure from the inside, but it should be even. If this pressure is going to be uneven, it's going to be collapsing very easily. It's something like, once again, if you're going to fill the water bottle with pressurized water, it's going to actually hold the water inside. But if you're going to have the water to be frozen inside the freezer, and in that case, you're not going to be expanding equally. You're going to expand from one side more than the other, and this will cause the bottle to be broken immediately. Okay, so we said that the impact of inflow design by using the side discharging system, which actually very useful to use the low energy of the gravity to empty the system. We can do it in multiple stages, but it should have something similar to these things. So this will be built in inside. This will cause that the system to be emptied in levels. So we're not going to have the case of the even loading to be occurred immediately. Okay, this is cases. Okay, you can see that here the inner pockets is going to slow down the process of the flow, and thus the unevening load is going to be acceptable. Actually, this software can be submitted, given to you, bring into work in the design of the Vint and Hooper. Many of the companies using this software to design the silos. Now, the problem we have with the Hoopers are the rat holding or the piping, the fuel flow, the arcing or the dooming, the unsufficient flow, the flushing, the endowment emptying, the mechanical arcing, and the tank consolidation of the taking. In the next few slides before we're going to take the break, we're going to have a look for each problem individually. We're starting with the rat holding. So that's what you're going to see from the top. The material has been built up. Okay? In the middle, all the material had a free flow. So the rat holding or the piping occurs when the core of the hooper is going to be discharged as in the fuel flow, but the stagnant sides are going to be stable enough to remain in place without flowing. And this will leave the hole in the hole down through the center of the solid stored in the bin, and this looks like a rat hole. So this will be the case where we're going to have the void is going to be in the middle, and we're going to have the stable mineral regions around it. The segregation process. So in the segregation process, we're going to have the coarse material to be built up on the side due to its weight. It's of course going to have something in the middle, but this one is going to be built up. When we open the hooper, the coarse material in the middle is going to flow first. but the one in this side is going to have something like the interlocking forces. When I say interlocking forces, is that holding each other, preventing from flow. And also some of the fine materials has been filled the cavity between the coarse materials and then solidified, and this will cause the system to be built up and not flowing. So we said that we have different size and density particles tend to segregate due to the vibration and the purification, some regulations actions of the small particles moving through the void spaces between the larger particles. So they will cause them to build up and thus interlocks. I think that it's going to be, to explain more for the people who've done the manufacturing subject, would be something like the case of the powder metrology. The small particles go through the cavities of the larger one and then hold them together. We had the arcing and the dooming. So we're going to have, if you're going to take a look from the outlet, you will see something like a spherical shape. It's a doom, actually. So this will give you an idea about why back in the old days they used to make the roof as a dome shape, because it can take the pressure from the outlet and hold itself. That's I think that you heard about the experiment of trying to break the egg by pressing on the side, because they have a dome shape. It's going to resist the force you have to add. So no flow due to the arcing or the dooming. The material is going to be cohesive enough that the particles from the arc bridge or the dooms that hold the overburden materials in place and stop the flow completely. We have the incomplete emptying. Once again, to have the material to be built up in the edges and prevent the whole system from being emptied. We have the unsubstantiated flow. The material will be flowed continuously as a massive flow, but the problem is going to be in very slow flow out. So what's happening, that flow is going to be too slow. The material does not exit from the hooper fast enough to feed the flow on the process. That's caused by, first, the outlet here, the outlet diameter may be too small to your material. Also, material not sufficiently permeable to permit the dilations in the conical sections. And thus, we're going to have the material to be flow as patches. So we're going to have some like flop, until the whole system is going to be empty. At least we're going to have the system to be empty, but it's not going to be meet the requirement of your process at the end. Now, let's say the requirement of this process can be either just emptying the silo to fill the truck. So your calculation is to fill this truck with the material within 30 minutes, but you end up with 1 hour. Of course, the accumulated time for every truck will cause extra cost for your process. We have the flushing, and usually the flushing is going to be happen because of the accessories we have down there. So the accessories is, I'm going to show you that actually have it in previous photo. Okay, can you see this screw there? It's called the feeder. So sometimes the feeder is going to blow up the air up inside the hooper, and this will cause the process of the flushing. So the flushing occurs when the material is not going to be cohesive enough to form the stable tube, but it's going to be strong enough that the material discharge rate is going to be slowed down, while the air tries to penetrate into the packed materials to loosen up some of the material. The resulting is we're going to have the sluggish flow of the solids that as the air penetrates in a short distance and freeing the layers of the materials, and the air penetrating the freshly exposed surface from the material. So once again, that's what's happening with the flushing. And the best process to get rid of the flushing is using the pressurized at the top. Usually this process is only going to be happening once again if the material is going to be light. So the air coming from the feeder is going to push the material up instead of take it down through the system. So as I told you once again, the best process, the best solution for this process is simply by sending, lock the whole system from the top, pressurize the system with the air, and this will push the materials to send it through the feeder to the process. An example for that can be once again the ash we talked about last week. Now, mechanical arcing, what we call the traffic jam, is that the materials start to build up and shape the plume shape. So usually the eccentric jam at the outlet of the pin, too many large particles competing for the small outlet. That's what will happen. And usually this will happen if we're going to have that the minimum outlet size should be 6 times multiplied by the diameter of the largest particle we have in this material. Usually we don't do it like that. We always do the calculation to do the way. Now the other one we have is caking or the diamond constellation. Many powders will tend to cake as a function of time, humidity, the pressure, and the temperature. I actually had an example today, and I wanted to take some photos at home. I have the protein powder, but it was stored in the container is made of paper. Well, it's the carton container. So due to the weather we have nowadays, today I tried to take out some of it, but it was actually caked. Within the time constellation, actually the humidity went in, temperature is quite high, and we have the things has been so defined. So once again, longer time of the storage is going to tend that the material is going to be built up, and thus it's going to be harder to empty from the containers. In particular, usually going to be a problem in the case of the film flow silos, which are going to be infrequently emptied completely. And we're going to have the size is going to be smaller, and of course, that means that the system itself is not going to be useful for the storage in the future. Let's have another 2 papers, then we're going to have a break. Actually, let's talk about the cone angles required for the chance of the Hooper massive flow. So the cone angle from the horizontal, that means if the Hooper is going to be like that, this will be the cone angle we're talking about, the one on the side. Okay, so it's going to be either 45 degrees, 60 degrees, 70 degrees, and 75 degrees. And actually, these are experimental data. So the cumulative percentage of the Hooper with the massive flow will be increasing from 0% up to 70% as we increase the angle by 30 degrees. So every types of massive flow have advantages and disadvantages. Flow advantages are, first, the flow is going to be more consistent. The effects of radial circulations, and the stress more predictable, and we are going to achieve the capacity to be utilized because it's going to be emptied by 100%, and then we're going to fill by 100%. And the most important thing that the first in is going to be the first out, because the level is going to go down from the top. That means the material is emptying from the bottom. So the material we had at the bottom, which has been put there for 3 weeks, is going to be emptied before the material which has been added last week. Now, we'll have these advantages that the wall wear is going to be higher because the flow is going to be faster. Of course, we're going to have a higher friction, and especially if we're going to have the abrasive material is going to damage the wall. High stresses on the walls, and more height is going to be required to achieve flow because we need to pressurize the material, and because usually the massive flow is going to be consequences of the gravity. Now for the film flow advantages and disadvantages, the only advantage we have is going to be that less height is going to be required. But the disadvantage we're going to have are the vat holding, the problem with these solids. First in will be the last out. Down constellation effects can be severe on the system. The silo may collapse. And we may have the flooding, and we may have reduction in all the effective storage capacity. So to design the hooper, you need to do either the measurement and we have to do the calculation. So the measurement is going to be for the powder cohesion and or the interparticle fraction. We learned that today. The wall friction, we learned that today. The compressibility and the permeability, we have tables for that. Calculate the outlet angle, the Hooper angle for the massive flow, and the discharge rate. So we are going to stop now and have a break for how much we need? 12 minutes. Come back by 7:20. Is that okay with you guys? I'm going to stop the recording here, and we're going to come back for